Hello and welcome to the first OpenRelay Screenside Chat. I'm Austin Roberts. The format for this presentation is that I have a slide deck that I'm going to be walking through, and we have 4 other people on a Google Hangout who are going to be asking questions if they have questions on things that I might not have fully covered. For those of you who aren't here live, this is going to be posted on YouTube at some point in the future. If you have any questions, please put them in the comments, and I will try to address them on a future Screenside Chat. So this particular presentation is going to cover OpenRelay as an introduction for developers. So if you are coming at this from the perspective of a market maker or somebody who would be interested in interacting with OpenRelay from a trading perspective, this probably isn't for you. This is more developer-oriented for people who are interested in developing on top of and inside OpenRelay. So some prerequisites for this presentation in terms of knowledge that I'm expecting you to have coming into this presentation is a basic familiarity with blockchain technology. Mainly this is dealing with what is distributed consensus, which is the main problem that Bitcoin initially solved. I'm expecting you to have some familiarity with Ethereum, which applies this concept of smart contracts on top of this concept of distributed consensus. Then I'm also expecting you to have a general knowledge of tokens on Ethereum, which are limited assets that are managed by smart contracts through the distributed consensus mechanism of the blockchain. The final point is that I'm kind of expecting people to come into this with general programming concepts. So if you're not a programmer, you're welcome to watch and listen, but there may be some things that you'll need to learn before this makes a whole lot of sense. Again, if you have questions, put them in the comments, and we will try to point you in the right direction towards resources for learning those general programming concepts that might not be covered here. So the first thing I'm going to talk about before I get into the meat of OpenRelay is what is 0x. There's lots of material out on the internet about what 0x is, some of it written by me. So 0x is an asset trading protocol on the Ethereum blockchain. So the way 0x works is over here you have somebody who's called a maker. This is somebody who has a token that they want to trade, and they want to find somebody who wants their token and will give them something else in exchange. So the maker, here's their token, creates something called an order, which is cryptographically signed, and we'll cover all of the details of the things that go into the order a little later. But they create this order, and they send it off to something called a relayer. OpenRelay, as you might guess by the name, is a relayer. We are open source, and we implement an open order book protocol. We'll cover what all of that means in a little bit. But basically, the maker sends their order to OpenRelay. Then you have a group of people called takers who can search OpenRelay for orders that they would be interested in filling. So as an example, there is one token on the Ethereum blockchain called WETH. WETH is wrapped ether, so if you've heard of Ethereum, you've probably heard of Ether. WETH is Ether treated as an Ethereum token, so that it can be traded through the 0x protocol. So another token, and we'll get into more detail on this in a little bit, is a token called ZRX that is associated with the 0x protocol. So say the maker over here wanted to trade WETH for ZRX. He creates an order offering WETH and asking for ZRX. This user over here searches for orders offering WETH and asking for ZRX because they have ZRX and they want WETH. Once they find that order on the relay, they can take that order and they can send it to the 0x smart contract on the Ethereum blockchain. The 0x smart contract will then see, okay, I have a signed order by the maker over here. The taker over here has submitted it to me. So that is both of them consenting to a swap of these tokens. So then the 0x contract will take this token from this guy, take this token from that guy, and switch them. So essentially, OpenRelay's role in this system is to connect the makers with the takers. So take the people who have tokens that they want to offer, and find the people who want the tokens that are being offered. And then the 0x exchange contract is on the Ethereum blockchain, and we don't have to be a part of that transaction. So some basic terminology for 0x. There is an order, which I mentioned earlier. This is an offer to trade one asset for another. There is a maker. A maker is the creator of an order. That's the person who, maker, creator, So the maker is offering the maker asset. In 0xv1, the terminology for this was maker token. In 0xv2, they support a wider variety of assets, so they have changed the terminology from token to asset. But the maker asset is the asset provided by the maker. I get a little confused on this. Is the maker getting the maker asset, or is the maker providing the maker asset? When you talk about maker assets and taker assets, the maker provides the maker token, the taker provides the taker token. So the taker is the person who searches the relayer, finds an order, and submits it to the blockchain to be filled. And again, the taker provides the taker asset. So another aspect of the order mentioned up here is that it can include a required fee to be paid by the maker and the taker. So in order for OpenRelay to list an order on our order book to be searchable by potential takers, the maker has to include with their cryptographic signature a fee to be paid to us when the order is filled. It costs nothing just to list an order on OpenRelay, but if you want to, once that order gets filled, somebody has to pay our fee. Our fee, as of right now, is 0.2 ZRX tokens, which came out to about 12 cents a couple weeks ago, and the price of ZRX fluctuates. In any case, the fees are not very expensive, and we allow for the maker and taker to split up the fee however the maker chooses, which we'll cover in a minute. But again, part of the 0x order is specifying who gets paid when this order gets filled and how much and by whom. The next point, these are some technologies that are a part of the 0x ecosystem managed by the 0x project team. And just to be clear here, I am not associated with the 0x project team. OpenRelay is building on top of the 0x protocol, but we are a separate organization from the 0x project team. So first of all, we have the 0x exchange contracts. So these are Ethereum contracts that exist to execute trades. And at some point, I may do a more detailed presentation about how all of these contracts work. I will probably wait until 0xv2 has gone mainstream, because if I right now, I'm going to be replacing that with a presentation for 0x version 2 in just a month or two. In addition to the exchange contracts, there's also this concept of the standard relayer API, which is often abbreviated to SRA. It is an API specification that includes both HTTP API endpoints and WebSocket APIs that are a standard way for different relayers to make their order books available to users. So the advantage here is, and there are at least a dozen different relayers out there. There's OpenRelay, there's Radar Relay, which Sam, who is on the call, works for Radar Relay. There's also the Ocean. There's LedgerDex. There's ERCDex. There are, again, as I say, about a dozen different relayers, and most of them, if not all of them, implement at least a subset of the standard relayer API, so that users who are interested in submitting orders to them or searching them for orders can write one tool that they can use to interact with multiple relays. The next 0x based technology is what we call 0x.js. This is JavaScript bindings for the 0x protocol. They help you deal with generating orders, cryptographically signing orders, submitting orders to the 0x contract on the blockchain. 0x.js does not deal with integrating with the standard relayer API. That is the place of 0x Connect, which is another library from the 0x project team. So these are JavaScript bindings for the standard relayer API. So if you wanted to build a tool that pulled orders from a 0x standard relayer and then submitted them to the blockchain to be filled, you would do that with a conjunction of 0x Connect and 0x.js. The last technology that I'm going to be talking about for now, and they do have several others that I haven't talked about and we'll get into in future presentations, is ZRX. So ZRX, as I mentioned earlier, is an Ethereum token associated with the 0x protocol. So when we talked about paying fees and that the order describes who is going to pay a fee and to whom and how much, those fees are being paid in ZRX. So as a 0x relayer, OpenRelay's only option for taking fees are to get paid in ZRX as the order gets filled. On one hand, it would be nice if we could take the tokens that are being traded or take things like Ethereum as the basis for our fees. But the way the 0x protocol is implemented, the easiest way for us to take our fees and the protocol-enabled way is to take them using ZRX. The peanut gallery has been quiet so far. Do you guys have any questions about the stuff I've covered so far before I move on from 0x technologies to getting into OpenRelay specifically? I'm seeing a bunch of shaking heads, so I'm going to move on. So now we're going to get into the details of OpenRelay. OpenRelay, as I mentioned, is an open source 0x relayer. We provide an open order book version of the standard relayer API. When I say open order book, there are basically two main models of providing a 0x relayer. The first, and this is what OpenRelay does, is we have an open order book. So anybody can send us orders, and anybody can take those orders and take them directly to the 0x exchange contract and fill them themselves. The alternative model is what they call a matching order book. So in that case, instead of a maker submitting an order and a taker taking that order, the maker would still submit the order, but then when a taker wants to take that order, they submit a corresponding order to us, and then we would take both the maker's order and the taker's order and take them to the exchange contract ourselves, so that that provides a handful of benefits in terms of usability. It allows us to kind of control who is taking what orders and make sure that we aren't going to have two people trying to submit the same order at the same time. But it also has the disadvantage that that is much harder for Ethereum contracts to integrate with. So with an open order book model, Ethereum contracts can take those orders and use them however they like. With an order matching model, really you have to go through an off-chain service in order to get those orders filled. So as I say, OpenRelay is an open order book standard relayer. Our code is implemented with a microservices architecture. The microservices are all written in Go and deployed with Docker. And our microservices architecture is built to scale. There are only about 3 services in our entire stack that cannot scale horizontally. And those 3 services that cannot scale horizontally are there to monitor for on-chain events that happen on the Ethereum blockchain. And thus, there's no real way that we would need to scale those horizontally aside from availability. So all of the services that we have, if we get a whole bunch of orders coming through at once, all of the services that we have as a part of OpenRelay can pretty easily be scaled horizontally. The exception is our database. But it would be possible at some point in the future for us to use a horizontally scalable database, but given our current scale, that seemed like a distraction. So some differentiators between OpenRelay and the other relayers that are out there. We are open source. To my knowledge, there are no other open source relayers. There was one that kind of got started at the ETH Denver hackathon, but to my knowledge, it has not gone anywhere since. OpenRelay is a developer-oriented service. So where most of the relayers are really targeting traders, we are trying to target developers who are building things that they want people to trade. So as an example, several months ago, there was this phenomenon called CryptoKitties. And CryptoKitties, if you're not aware, is basically a way that you can buy, sell, breed cats on the Ethereum blockchain. Now, they're not real cats. They are pictures of cats. And they have different properties, like they can be striped or spotted or solid colored, and they can be lots of different colors. And they have different properties like what generation they come from, and all of those things make them in some ways desirable, and that people want to trade them. So when CryptoKitties came out, they were implementing a new token standard called ERC 721, which is for things that are tokens that differ from one token to another, and we'll get into the details of that in a little bit. But 0x at that time was not capable of providing a trading platform for CryptoKitties. So CryptoKitties ended up implementing their own trading system, which ended up eating a huge portion of the capacity of the Ethereum blockchain for several weeks before people stopped caring. One of our goals with OpenRelay is that in the future, the person who develops the next CryptoKitties, that's something everybody wants to have and wants to trade, instead of building their own on-chain trading service, that it will just make blinding sense for them to implement their trading service on top of OpenRelay because it's there and it's ready for them to use. Another differentiator is that where most relayers have a list of tokens, and more specifically token pairs that they will allow you to trade, OpenRelay will allow you to trade any tokens in any token pairs. So, most relayers have an Ethereum market and maybe a DAI market, where those are the two coins that you can use to trade against other things. So if you wanted ZRX, you would have to either use wrapped ether or DAI to purchase it. OpenRelay, we would allow you to trade ZRX tokens for BAT tokens if that's what you wanted to do, or ZRX tokens for CryptoKitties if that's what you wanted to do, once we support CryptoKitties, which should be very soon. Again, we are being developer oriented. We're not necessarily expecting all of the people who build on top of OpenRelay to allow trading of arbitrary token pairs, but in order to enable developers to better build against our system, we are allowing trading of any arbitrary ERC20 token pairs. The next differentiator is that we have flat fees. So where most relayers try to charge a ZRX fee as a percentage of your total trade, we charge 0.20x no matter what you're trading. So at least right now, our fee is 0.20x. That will fluctuate depending on the value of ZRX. But right now, regardless of the two tokens being traded, our fee is the same. Doesn't matter what the quantity of the tokens are. We basically look at it as we are a publisher dealing with orders that have been provided to us and are being searched by takers. We have certain responsibilities when it comes to dealing with those orders to make sure that they are valid orders that are fillable on the blockchain. But none of those tasks that come to us as the result of an order scale any differently based on the value of the order. The cost for us to process a very cheap order are the same as the costs to us to process a very expensive order. So we don't make a distinction in what we charge. We charge our fee based on the order. And so if you're trading, millions of dollars worth of tokens, you're paying a completely insignificant fee. Whereas if you were trading, essentially valueless tokens, the fee will become a fairly significant portion of what you're paying. We also offer a flexible fee structure. So where most relayers will say something like, the taker is going to pay 70% of the fee and the maker is going to pay 30% of the fee, we are saying so long as the maker fee plus the taker fee adds up to 0.2 ZRX, we will accept your order. Again, the part of the reason that we are structuring it this way is to be a good developer-oriented service. So if a developer who is building on top of OpenRelay wants to say that the taker is going to pay 70% of the fee and the maker is going to pay 30% of the fee, they are free to do so. But by offering the flexible fee structure, a developer might decide, on my application, the makers are going to pay all of the fees, or on my application, the takers are going to pay all of the fees. Or they might leave it up to the maker to decide whether the maker or the taker is going to pay the fees. We don't really care so long as we get our 0.2 ZRX. I threw this in there. So many of our design decisions are about what is going to be good for developers and attracting developers. So in the words of, oh no, I'm blanking on his name. Brant, I can see it on the tip of your tongue. Steve Ballmer. Steve Ballmer, developers, 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 developers. All right, so we are about to announce an affiliate program, and by the time this video is publicly available, it will probably exist. We are going to create an affiliate program that anybody can sign up for. When an affiliate signs up, they will get their own fee recipient contract. Once they sign up, orders that get submitted to OpenRelay with that fee recipient contract listed as the fee recipient for an order will be accepted and listed on OpenRelay. When that order gets filled, the affiliate contract will get the fee. So the affiliate contract's address is what gets listed as the fee recipient on the order. And so when that order gets filled, the fee recipient contract gets paid. The contract will split that fee 80% to the affiliate and 20% to us. So as I mentioned earlier, we are a very developer-oriented platform, and developers have lots of options when they're building an application in terms of how they want to handle their trading platform. So they could go the CryptoKitties route and they could write their own. They could use OpenRelay.xyz, which is our platform as a service, and not have to worry about the operations. They can just send their orders to us and know they're going to be there when their takers try to search for them. Or, since we're an open source project, they could take it and run it themselves. If our fee percentage were too high, then any of our affiliates are going to go, oh, I'm not going to pay that. I'll just run it myself. So in order to be competitive and attractive to developers, we are giving them 80% of the fee, and we are taking 20% for the overhead of operating the order book. Our hope is that that will be a very attractive deal to a lot of developers who will then decide, I'm not going to build my own order book platform, or I'm not going to bother running my own copy of OpenRelay. I'm just going to put stuff on the public OpenRelay and let them deal with scaling an order book and pruning an order book and all of that other fun stuff. So now we're going to start getting into the high-level implementation of how OpenRelay works under the hood. So this is our architecture diagram, and this will be popping up again and again over the next several slides. First, I want to give a shout out to Mohoff from Gitter, who sent me this architecture diagram. I did not write this architecture diagram. Before I started OpenRelay, I had something that was very similar to it, but I let it get out of date as several services were written and rewritten. And then a couple of weeks ago, a guy approached me on Gitter, who I had been talking to and helping through several issues. But he approached me on Gitter and said, hey, I wrote this, or put together this architecture diagram. I thought you might like to have it in case other people are looking for something about it. So anyway, I have made some slight modifications to it since he gave it to me, but this is generally the architecture diagram that was put together by Mohoff on Gitter. So, also, if you're not on Gitter, that is a good place to have public conversations about what's going on OpenRelay. It's a good place to get troubleshooting help. So the link is on our main homepage. If you go to openrelay.xyz, it has a link to Gitter. So the first service, and I'm going to go back to the diagram. The first service, as we have a user who submits an order, that order first goes to our ingest service. So the ingest service is a public-facing API that receives orders from the users. The ingest service validates some basic attributes of an order before it responds to the user. The things that it validates are the order format. So is the order well-formed? Is it something that we can parse and know what it means? The second is it on a supported exchange? So if the exchange contract is not one that we're monitoring, then we are not going to accept your order. The third point is the expiration date of the order. If your order is already expired, we're going to reject it. If your order expires 1,000 years into the future, we're going to reject it. If it's anywhere in between now and 1,000 years from now, we will accept it. Now, the reason we reject orders 1,000 years into the future is not actually that we care about having orders that are going to exist for that long. It's that we've had several people who have made the mistake of thinking that the order expiration timestamp is in milliseconds when it's actually in seconds. So by rejecting orders that are more than 1,000 years into the future, anybody who mistook seconds for milliseconds is going to have their order rejected and not get listed, and resulting in them ending up with an order that's going to last way longer than they intended. The next point that we validate at the ingest service is the signature. So as I mentioned, orders are cryptographically signed. We make sure that the signature on the order corresponds to the maker indicated by the order. If it does not, then we're going to reject the order. And finally, fees. So as I mentioned earlier, orders can include fees for the 0x relayer. If the fee on the order, the maker fee plus the taker fee, does not add up to 0.2 0x, at least as of today, then we are going to reject the order at the ingest time, and the user will see that they'll get a message that says, oh, you need to add a fee that adds up to at least this amount. The ingest service does not validate properties of an order that have to be validated on the Ethereum blockchain. So this is things like, has the order been filled or canceled? And does the maker have the required tokens to fill this order? The reason for this is we want our ingest service to be nice and responsive. We don't want it to go down because it's overloaded. We don't want connections to be hanging open for a long time because that makes it more likely to be overloaded. We want it to be able to respond to orders very quickly. And the Ethereum blockchain, the RPC servers that allow us to interact with that are a bit finicky. They don't scale very well. And they tend to be one of the touchier parts of our system. So when we get an order from a user via the ingest service, we put it onto a queue to be validated later and eventually make its way to our order book system. The queuing system that we're currently using is Redis. At some point, we may switch over to using Kafka as a queuing service. The main reason that we went with Redis from the outset was that Amazon Web Services, which is the hosting platform that we use, provides Redis as a service, so we could simply set one up and forget about it, and that has served us pretty well so far. So back to the architecture diagram. After an order comes in through the ingest service, it's going to go to the fill updater service. So the fill updater service receives an order on a channel in this case being a Redis queue. It checks the blockchain to see whether that order has been filled or canceled. Now, we have an optimization using something called a Bloom filter to avoid RPC requests if we can. So the vast majority of the time when an order comes to us, it is a brand new order that has never seen the blockchain. It's something that somebody has just generated and sent straight to us. It's not going to be on the blockchain. So this Bloom filter allows us to probabilistically check whether or not this order could be filled or canceled at this time. So if the Bloom filter says that this order is not on the blockchain, then that order is not on the blockchain. If the Bloom filter says that this order is on the blockchain, then that order might be on the blockchain. If it might be, we run an RPC query to find out for sure whether that order has been filled or canceled. But basically, the Bloom filter allows us to avoid the vast majority of the fill updaters RPC requests with an absolute certainty that we don't need to make that RPC call. And it might require us to make some RPC calls that we didn't actually have to make. But Bloom filters are a really neat data structure, and if you haven't read about them already, you probably should. I'm not going to cover that here. So after the fill updater has determined whether the order has been filled or canceled, it publishes the updated order onto another channel in order to be consumed by the next service. So the next service, as we can see from our architecture diagram, is the fund validation service. So the fund validation service checks the blockchain for maker balances. So the person who made this order, they have to be able to pay the amount of tokens that the maker said they're going to offer, or we're not going to list their order. Even if they had a partial amount of the orders that of the tokens that they said they'd offer, if they don't have the full amount that they need in order to complete that order, we're not going to list the order. Likewise, the makers have to set allowances for the 0x exchange contract to pull those tokens from their account. If they have not set those allowances, then we consider their balance to be 0, because as far as the exchange contract is concerned, they don't have a usable balance. So the fund validation relay will discard any orders where the funds or allowances are inadequate to for the maker to fill the order. That also goes for the fee token. So it's not just the order that they're offering the taker, it's also for the token that they're offering to us. So if they promise that they're going to pay the full 0.2 ZRX and they don't have 0.2 ZRX, or they don't have allowances set for 0.2 ZRX, then we are going to reject their order and not list it because this order can't actually be filled. So the fund validation service, the first time it completes, it is going to pass an order off to the delay relay. On the second pass, it's going to pass it off to the indexer. So if we look here at our architecture diagram, something comes in from the ingest service and it goes to the fill updater, then it goes to the fund validator. The first time it's going to go to the delay relay, and we'll cover what this is for in a minute. But after it goes from the delay relay, it goes back to the fill updater because there's just been a delay. So we have to recheck the order. Goes back to the fund validation service. And then once it's been through twice, it goes to the order indexer. So what is the delay relay for? At some point in the future, OpenRelay will sell limited access to new orders. So basically, if people want to pay money to get early access to orders that have not been published for everyone else yet, we will take their money and give them that information. Those orders will be public 2 blocks after we receive them. So that is there to give the people who are paying for early access 2 blocks to get an order onto the blockchain saying, I want to fill this, and get their order filled before the public finds out about those orders. So the delay relay, and there's actually 2 delay relays. It goes to the first one, then it goes to the second delay relay, but I mushed them together for the purpose of this diagram. The delay relay holds orders for 2 blocks and then sends them back to have their funds rechecked before they go off to the indexer. So at this point in the architecture diagram, we have gone from the ingester to the fill updater to the fund validation service to the delay relay, back to the fill updater, back to the fund validation service. I'm not going to cover those services again. They don't need more slides. They do the same thing the second time. And then they go off to the order indexer. The order indexer shoves orders into a database. It's pretty simple, nothing very complicated about that. I should note that we support MySQL databases and Postgres databases. In theory, we could support probably a handful of others, but right now we actively test against both Postgres and MySQL. And we run MySQL in production because Amazon offers AWS Aurora at more scalable levels for MySQL than they do for Postgres. It's a very nice managed database service and takes a lot of worry off of us. Again, the OpenRelay team is very small, and so where we can take advantage of a managed service and not have to worry about something, that's what we do. So here, we've made it to the order indexer, and this here shows an indexer. This indexer isn't really a microservice so much as a module inside the Go code that is kind of shared by all of the order indexer and these other things that need to shove stuff into the database. Those all go through this indexer module, and then that gets fed into the MySQL database. So the next point that I'm going to talk about is after an order has been indexed, it goes to the MySQL search API for when people are searching for it. Oh, I guess I had a slide on MySQL. I kind of forgot about that. MySQL holds orders. We also support Postgres, and we use Aurora in production. I already covered all of those points, but I wasn't looking at the slide when I did it. So yeah, back to the search API. So the search API, again, is a public-facing API. It's something that anybody on the internet can search. It provides an order search API defined as the standard relayer API. when a user submits a query as formatted by the standard relayer API, the search API retrieves the orders from MySQL. We also have this weird thing going on with a block hash parameter that is not a standard part of the standard relayer API. So basically, if you run a search on the standard relayer API and you don't have a block hash parameter, our search API will redirect you to the same page that you were already on and add in a block hash parameter. That block hash parameter means absolutely nothing, and the API only cares that it's there. However, because we use AWS CloudFront in production, that block hash parameter allows us to have those search results cached indefinitely. And we increment the block hash, or we change the block hash parameter every time an Ethereum block is mined. Since we have the delay relays in place and things only make it into our database when blocks happen, then we can indefinitely cache an API call that includes a block hash parameter. So every time the block increases, the block hash parameter changes and our cache gets invalidated. But the end result is, if we have a bunch of people on the internet all querying us for the same thing, they all end up getting that block hash parameter, and they all end up hitting CloudFront instead of hitting our backend servers, allowing us to scale a little bit better. So, you know, the only place that would particularly matter is if you were using some kind of REST interface where when you ran a query, it did not honor redirects. So if you just use the standard relayer API and don't follow redirects, you're going to have a bad time. But so long as you follow redirects, you can interact with it exactly like the standard relayer API, and you get to take advantage of our caching. So moving on from the indexing side of our microservices, now we're going to talk about our monitoring microservices. So our monitoring microservices react to blockchain-based events. So the Ethereum blockchain has this really nice system of events where when certain types of things happen on the blockchain, they emit events that are really easy to monitor for. And that allows us to prune our order book, that is to say, remove orders that can no longer be filled without having a whole lot of extra overhead. So I'm going to go over the basic architecture of our monitoring services. Our monitoring services are designed to minimize RPC calls. As I said when we were talking about the fill updater, our RPC servers are really finicky. So we try to avoid hitting them any harder than we have to. So the way we have this structured is we have a block monitoring service that watches the RPC server for new blocks. Then it publishes those blocks through a system of Redis queues. And the other monitors that need particular events watch the block monitor to figure out when things have happened that they're going to be interested in. So we've talked about all of the services over here on this side of the page. Now we're going to start talking about these services on this side of the architecture diagram. The Ethereum node is represented up here, and it is the finicky service that I was talking about before. So the block monitor queries the blockchain for new blocks periodically. I believe that is configurable as a parameter to the service, and I think in production we have it set to query the blockchain for new blocks every 5 seconds. The block time on Ethereum is somewhere between 10 and 15 seconds. So checking every 5 seconds means that we don't run too many extra queries, but we usually get the block pretty quickly after it happens. Once the block monitor finds a block, it publishes messages containing the block number. So the latest block number is somewhere in the 5 millions on the Ethereum blockchain. It includes the block hash, which is a unique representation of the hash that is independent of the block number. And it includes the block Bloom filter. So we talked about Bloom filters earlier and how they're really cool. Well, Bloom filters are also used by the Ethereum blockchain to allow services that are interested in what events happened in a block to check the Bloom filter for whether or not this block includes that event that you said you're interested in. So by checking the block Bloom filter, our other services are able to determine whether they need to go to the blockchain to ask for specific events before they run RPC queries against the blockchain. So for some of the services that don't get events very often, they only have to run RPC calls once they get a block that already has an event that they have indicated they're interested in. So anyway, that's the block monitor. The blocks from the block monitor go to the fill monitor, the allowance monitor, and the spend monitor. There's actually a couple of other things in our version 2 architecture that also consume from the block monitor, but these are the ones I'm going to be talking about for now. So the fill monitor checks the block Bloom filter for 0x fills. So again, this Bloom filter came in the message that it got off of a channel. So it is able to check whether or not this block includes any 0x orders that were filled before it has to make RPC calls to actually get the filled orders. If there's no filled orders in this block, the Bloom filter will say there are no Bloom filters. The Bloom filter will say there are no 0x fills in this block, and we will not make any RPC calls. If we do find filled orders, then we publish a fill record onto a channel for each and every one of those RPC calls. Sorry, for each and every one of those filled orders. Those fill records basically say this is the order that was filled, and it includes the order hash. It includes how much of the order was filled, because orders can be partially filled, and it includes whether or not the order was canceled by this request for the fill monitor. We could have had a separate cancel monitor, but the fill monitor and the cancel monitor would have been basically the same thing, so I just did them in the same microservice. From the fill monitor, the fill records go to the fill recorder. So the fill recorder watches for fill records, and it updates the fill amount on the orders in MySQL. So we are monitoring the 0x blockchain for every 0x order that gets filled. And then we are searching our database for any corresponding orders and updating our database record to show that they have been filled or canceled. The likelihood is that we don't actually have that order because we're a small fraction of the orders that get filled on the blockchain. But either way, we check every order that comes through to see if we have it in our database. Next, I believe we're moving on to the allowance monitor and the spend monitor. Now, both the allowance monitor and the spend monitor feed into the record spend consumer, and we will cover that, see what that looks like in just a minute. So the allowance monitor checks the block Bloom filter for every block that comes through for any token allowances that are set targeting the 0x exchange. So it does not matter whether we have orders for this particular token. Any Ethereum block that includes any token setting an allowance for the 0x exchange contract is going to alert this allowance monitor. We then make an RPC call to get the complete set of allowance, and then we publish what we call a spend record to be consumed by the spend recorder. The spend record includes the token that was spent or approved, the user who spent or approved that token, and the balance or allowance of that token after the transaction happens. So this is all the information that we need in order to determine whether any orders created by that spender of that token are still going to be fillable after this transaction. Likewise, we have a spend monitor, and this one gets pretty busy. So it checks the block bloom filter to see whether any tokens have been transferred on the Ethereum blockchain. And because token transfers are a huge part of what the Ethereum blockchain does, we almost always find that in every block there have been a dozen token transfers. So that being the case, it ends up making an RPC call to get the details of every token that has been transferred. So the event for the token transfers tells us who transferred what token, but it doesn't tell us what their final balance is afterwards. So then we have to make another round of RPC calls to get the user balances, and then we publish a spend record that tells us who just spent some tokens, what their balance is after they just spent them, and whatever the third piece of information was. What token they spent. So spend records, whether they came from the allowance monitor or the spend monitor, go off to the spend recorder. The spend recorder updates any orders affected by that spend to set their status to unfunded if the maker of that order no longer has sufficient funds to complete that order. So if the order's remaining amount exceeds the spender's balance, then the order is removed from our order book. Orders that are no longer fillable are marked as unfunded, which is a status in our database. And once an order is listed as unfunded, it will not be returned in our search results. If you know the order hash, you can still go look it up, but otherwise, you're not going to be able to get any information about that order. So that is it for today's Screenside Chat. Next time, we will be talking about OpenRelay and how we use Docker. We will be looking at the OpenRelay development environment. And if you want to follow along and actually try to have OpenRelay up and running by the end of the presentation, on your laptop or desktop, have Docker installed when you come to the Screenside Chat, and have OpenRelay checked out from the link below. So before I close off this presentation and stop broadcasting for the people who are going to watch this someday, do those of you in the peanut gallery have any questions?
Not one. So you mentioned that orders could be partially filled?
Yes.
So what happens fee-wise when an order is partially filled?
They pay a comparable percentage of the fee. So if it's 50% filled, they pay 50% of the fee. If it's 10% filled, they pay 10% of the fee.
Okay.
But that same order might be filled multiple times. If it's partially filled, it could be filled to 10% 10 times. And from our end, it really doesn't make that big of a difference to keep an order in our order book once we've done that initial validation process.
Okay.
So you mentioned the validation process will reject orders, or at least throw them out after the ingest has accepted the order, since the ingest does a simple validation without checking balances and etc. Is there any notification for orders that have been tossed out?
Not at this time. So one thing I would like to get on our roadmap to do at some point in the future is if you take that order hash, be able to go to our API somewhere and be able to get the status of that order and why it was rejected. Or as it stands, since we currently just implement the standard Relayer API and don't have any extensions on top of it, there is nowhere in the standard Relayer API for that to go. With 0xv2, we will probably be adding some additional APIs, and that will probably be one of them. Any other? Oh, one of the other things I want to note on the points that we reject orders for. We reject orders because they don't have sufficient funds, or the order has already been filled, or something like that. Those are statuses that can change after the order was submitted to us anyway. And in those situations, we wouldn't be able to respond to the user who submitted it. I would still like to cover those with an API call that, hey, I know this order hash should exist, or perhaps a way for a maker to query for, show me all of the orders I've made, whether or not they're still fillable. But based on the current standard Relayer API, there's no way for us to offer that, but we will probably do so in an extension in the future. Any other questions?
You've talked about limited RPC calls that you can make to the Ethereum network.
Yes.
Can you add more details about that? Because I know that we've talked in some details about this, but no one else is very aware if they're watching this for the first time.
Talk in detail about what exactly?
The limited state of RPC calls you can make to the network because it doesn't scale well.
Well, yeah. So, and this is certainly a conversation for another Screenside chat. This is something I could go into at length for hours. But basically, the Ethereum nodes that serve your RPC requests have, at this time, any Ethereum node that you're making RPC requests to basically have to be a peer-to-peer Ethereum node. So they are getting every Ethereum block and doing block validations. They may be doing transaction validations unless they're light nodes. If they're light nodes, they're not doing block validations, but then they have a whole bunch of additional network overhead for every query that you run against them, because they have to go get that information from a peer on the peer-to-peer network. What Sam is alluding to, I think, is that we have a project that OpenRelay and Radar Relay are kind of collaborating on to create a system of like streaming replications, so that you would have one Ethereum node where it's doing the peer-to-peer thing and communicating with all of the other peers, and then everything that it writes out to its LevelDB database gets put onto a Kafka stream that gets replicated out to additional Ethereum nodes, which don't have to worry about all of the block validation and transaction validation and maintaining peer-to-peer connections. That they can just sit there and serve your RPC requests, and they can be scaled horizontally. So as many RPC requests as you need to run, you're welcome to run. This is a project that you can find on GitHub. So if you look at the GitHub link that I have on the screen, instead of being github.com notegio/OpenRelay, it would be github.com/notegio/go-ethereum. That is a fork of the Go Ethereum project, and we are trying to get a version of the Go Ethereum client running with streaming replication. It's a project I have not had a whole lot of time for. I'm hoping that now that I've freed up some time from some of my consulting work, that I will have more time to work on that and get that working more reliably. If anybody else is interested in participating or contributing to that, I would embrace the help, and I would be happy to talk about the architecture for that. That's probably a subject for a Screenside Chat sooner rather than later. It won't be next week's, but it might even be the week after that. Any other questions? All right.
Are you planning to do a deeper dive into the coding and design decisions you've made for some of these microservices and your microservice architecture?
Yes, definitely. I'm planning to do kind of a breadth first approach. So to try and get a high level view of all of the pieces that you need to understand how they fit together before I get too far down into the depths of the implementations of in any particular service. Yeah, my intent with these Screenside Chats is definitely to go into the implementation of a lot of the microservices.
And then the last question I have is, how good is the developer documentation for people to contribute inside the GitHub repo?
Not great. That is something that the people on this call have access to me on a regular basis. If you have questions, by all means, ask me. I would love it if you guys took that and helped add to the developer documentation. One of the things I have challenged Jeremy to do is go through and write doc strings for all of the methods that I have left undocumented throughout OpenRelay. And yeah, I would love to get better documentation going. It's just there's a ton of stuff going on. I'm proud of the test coverage that OpenRelay has. I'm not proud of the documentation that OpenRelay has at this point. I'd like to be, though. Hearing no other questions, I'm going to stop the broadcast. My hope is that we will have another Screenside Chat at the same time next week. Thank you, guys.
Thank you.